Today's lesson has a high NQ, a high nerd quotient. Some neat stuff here. Some neat applications. And Brendan, I'd love to talk about the first one, which is called the current balance. It talks about how you can use electricity and magnets to create a very, very accurate scale. But for interests of time, I'm going to pass on that. It's an application, but I'm not going to test you on it. I am, however, going to assess you on the second application. So can you go to where it says the cathode ray tube revisited? Televisions, not the thin flat screens, but the TVs that you guys had until you were about 10 or 11 years old. So you grew up with these still. You may recall we said for a cathode ray tube, for a television, it was basically an electron gun, and we were using electric parallel plates, positively and negatively charged, one set like this and one set like this, to deflect them left, right, up, and down. We don't actually, because the parallel plates had to be fairly long, and we've always wanted to try and miniaturize things. So what they went to a long time ago, instead of parallel plates, they said we can also deflect them with solenoids, in particular, two solenoids in this arrangement here. So take a look at this picture. We have an electron gun. The electrons, Tyson, are coming out of the page towards us. We're going to use our right-hand rule, but our right-hand rule doesn't work for electrons because those are negative. So if electrons are coming out of the page towards us, which way will we point our thumb? Which way would protons be traveling? Into the page. So when we start to assess this, you'll be pointing your thumb kind of into the page at an angle. Okay? I want you to look at this solenoid right here, solenoid N. Imagine holding it in your hand. Curl your fingers in the direction of the current. Well, I didn't tell you which way the current is going, Carissa, but it seems to me you can either, Carissa, hold it like this or like this. It seems to me there is either, don't write this down, I'm going to muck up this diagram, a north pole there, or, I said don't write this down, I'm going to muck up this diagram, or a north pole there. Just for the sake of argument, let's put our north pole there and our south pole there, which would mean that the current was running that way. Just for the sake of argument, let's do that. So you can write that down there. What direction is the magnetic field? Well, magnetic fields always point from what to what? North to south. And what I want you to notice is right here, the magnetic field is pointing to the right. Right where the electron beam is, the magnetic field is pointing to the right. Which way would the electron get deflected? So now let's use our right-hand rule. Are you ready? Let's point our thumbs into the page, because that's an electron going out of the page, into the page. And the magnetic field is pointing to the right. If I bend my hand a little bit, which way is my palm pointing? Down. It turns out the horizontal solenoid can deflect it down, or Hisham, if I reverse the current, which would put a north pole there so that the magnetic field is pointing that way, it could also deflect it up. Solenoid N can deflect it, but it does so needing much less space than those parallel plates did. Your TV can be more compact. And it's kind of weird, but a horizontal solenoid deflects it up-down. You know what this vertical solenoid does? It deflects it left-right. You can play around with your right-hand rule to convince yourself of it, but solenoid M deflects it. Which now means, Tyson, we can deflect that electron and pinpoint it with accuracy. We can put it anywhere we want to. This is how you painted the inside of a television screen, and then the phosphorescent color would glow, and that's where you got your black and whites, your gray scale. Color, it's 3 different beams with 3 different types of phosphorescent paint. Red, blue, and cyan, I think. It says show magnetic deflection. I already showed you the video where it had on the television screen a picture of a clock, and we brought in the magnet, and the screen went all wonky. I'm going to ask you some questions on your test, multiple choice probably, something like, well, heck, example 1. Example 1 says an undeflected cathode or electron beam strikes the center of a cathode ray tube. So before we turn anything on, it starts right and hits right there. Don't write that down. That's where it hits. We put the solenoid and we turn it on. When we turn the solenoid on, it hits at location X. What changes to the magnitude and direction of the current in the solenoid would cause the electron beam to strike at location Y? Okay. When we first set this up, it was getting deflected downwards. Which way is it getting deflected to go to location Y? Upwards. What would do that? Switching the current. So I'm going to put a no, yes down that column, and I know the answer is either B or D. In situation Y, are we deflecting it more than the original or less than the original? Alex, more than. What do you think would do that? A weaker current or a stronger current? Convince me. Remember we said this last class. The magnetic field for a solenoid was equal to the permeability of free space, Ni over L. N was the number of turns of wire. Have we actually changed the solenoid, or is it the same? L was the length of the solenoid. Have we actually changed the solenoid, or is it the same? I was the amount of current, and if this gets bigger, what's going to happen to your magnetic field strength? Bigger. What's going to happen to your deflection? Bigger. You're right. Increase, increase, no, no. Gotta be B. Does that make sense, Itzel? Or I could ask you a question like this. With the electromagnet turned off, electrons in the cathode ray tube strike dead center. When the electromagnet is turned on, where will the electron beam now strike the screen? I first have to figure out what's going on in that solenoid. If I zoom in, it seems to me that's positive, that's negative. I think the current is going this way and going over the top. It's a lousy photocopy. It's the best I could get. But I think if I was holding the solenoid so that my fingers were curling in the direction of the current, would I hold it this way with my thumb down, or would I hold it this way with my thumb up? Carissa, I don't know. Trying to figure out which way. If I want the current to curl over the top, like this, yes? Yes? Not like that? Like this? Yes, Eric? I'm positive that's north and that's south. Which means the magnetic field lines go like this. Which way do magnetic field lines always point? From what to what? From north to south, which means in the electron beam, what direction is your magnetic field? Up, down, left, or right? Look at my picture. What direction is the magnetic field right there? Up, down, left, or right? Up. There's an arrow right there. Up. Okay, you ready? Right-hand rule. Which way is the electron beam coming? Look at the picture. Which way is the electron beam coming? Out towards us? We don't do electrons. Which way is the proton, our imaginary proton beam? So point your thumb into your paper. I would point at my computer screen. Which way is the magnetic field according to this question? Where the electron is? What did you say? Up. So extend your fingers up, like a high five position. Which way is this electron going to get deflected? Location 1, 2, 3, or 4? Location 4. Location 4. So one application of this is the cathode ray tube, TV screens, and you grew up with those. This is another very cool application. It's the electric motor. The electric motor. And this one is easier to show with the animation. Hello, animation. No, there. So here is our electric motor, and I'm going to pause it. Boom, right there. Now, unfortunately, I can't zoom in. But if you take a look at this, here's the positive current. At the top right here, which way is the current flowing? It seems to me that way. Yeah? Which way is the magnetic field? Well, the blue arrows are telling you the magnetic field is pointing which way? Down. So point your thumbs like that. Magnetic field, you got to kind of bend to go down. Which way will the top half of this wire feel a force? That direction. What about the bottom? Well, can you see the current's going to come all the way around, and when it gets to the bottom of this wire, this is a simplified motor. It's using a single turn of wire called an armature. Eric, in real life, you'd have several thousand turns to amplify the effect, but it's hard to keep track of, so here's a single turn of wire. Can you see in the bottom, I have the current going this way. I point my thumb this way, hands down in the direct magnetic field. The bottom's going to get pushed towards me. The top's going to get pushed away from me. What that's going to cause it to do is spin. Unfortunately, because we're using direct current, in half a spin, this would end up there, this would end up there, and it would come to a jerking stop. Because now on the bottom it'd be getting pushed that way, and on the top it'd be getting pushed this way. It would go. What we need is a way to always have the current flowing on the top that way, and always have the current flowing on the bottom that way. So what we do is we have this middle section right here, this piece of metal. I'd like you to imagine a hamburger. Now remove the patty. So you just got the bun, but with a gap between it still, and make that bun out of metal. And that's what you have here. It's called a split ring commutator. It's a fancy word. What it does is it allows the current from the positive always to be going to the upper half. It allows the current from the negative always to be going to the lower half. And there comes a split second when there's no current right there, but the momentum of the motor keeps it turning long enough to come up. So there's a split second with no current, but the momentum of the motor keeps it turning long enough to get the current to go again. Let me show you a different animation here. We're back. So here's an explanation. If you were looking right down the end of this armature, by the way, some words you'll need to recognize. They will use the word armature on your test or in your homework, so will I. That's the coil, that's the wire that's spinning inside the motor. Our simplest case, Andrew, is a single coil of wire. That's a terrible motor. The more coils you put together, the more efficient it is. Okay. The split ring commutator, that's this gap in these two pieces of metal that allows from a direct current you to get an alternating current coming out of it to keep the motor spinning. Brush contact. Okay. So if you're looking down the end, you have current coming out of the page towards us, magnetic field to the right, current coming out of the page towards us, magnetic field to the right, it gets pushed up. Current going into the page away from us, magnetic field to the right, it gets pushed down, and there's your rotational torque, your spin. Side views, blah, 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 blah. Electric motors come in all sizes. Some are very tiny and drive toys. Others are huge and drive trains or buses. You find them in toy trains, automobiles, clocks, wheelchairs, streetcars, can openers, cement mixers, furnace fans, you find them everywhere. They dominate your life. Oh, are electric motors becoming more important or less important? You guys watch the news. What do you think? Yeah, in fact, probably the odds are you guys will be the generation where somewhere the tipping point occurs where there are more electric cars on the road than gas cars. Probably. We're getting better at building them more efficiently, etc.